EEE145, Chapter 4, Symmetrical Components, Part 2. Okay, last time we talked about the basics of symmetrical components. This time we're going to take symmetrical components and do pretty much fault analysis, right? And we're going to talk about the entire steps of going through it. So remember, fault analysis, the goal is to find the fault current at the end of the day, right? Now, it's an unbalanced system, so we're going to have to use symmetrical components to figure out the fault current. Now, the first step for any fault analysis is we have to build the sequence impedance networks. There's going to be 3 of them: positive, negative, and zero sequence networks. So we got first, let's build a positive sequence network. This is pretty much from the one-line diagram that you have. All right. So one-line diagram and all your positive sequence impedance. Positive sequence impedances. Okay, so a lot of times your equipment and the manufacturer will give you impedance in different sequence components. For example, a negative sequence impedance network is, again, you draw from the one-line diagram. So one-line diagram is your basis. And we're going to use instead negative sequence impedances, right, which could be different. Lastly, we're going to build the zero sequence network. And again, this is from your one-line diagram. And we're going to use the zero sequence impedances. Now, we'll also most likely use the ground network, right? Because we're doing fault analysis, the ground might have a play in the amount of current that's available, right? And this is always taken into account in your zero sequence network. Okay. So here, after we have all 3 of our sequence networks, we need to combine them in a particular fashion so that we can calculate our fault types. So we need to calculate fault current based on fault type. Okay. So different fault types will use different networks configured in different orientations, right? So step number 1, get your one-line diagrams, get your impedances, build 3 separate networks. Okay. Next, after all 3 networks are built, we're going to combine the networks together, either in series or parallel, depending on the type of fault we want to look at. Now, every book is going to have these diagrams to show you what a 3-phase fault network looks like: a phase-to-phase, a double line of ground, single-phase fault, right? I don't expect you to memorize this stuff. It's pretty much a reference chart somewhere on your desk, or you just have this open whenever you need it. Now, a 3-phase fault is balanced, right? Because all 3 phases are faulted. So you'll actually see all 3 fault currents the same magnitude with 120-degree phase shift, right? Because it's purely balanced, you only need the positive sequence network. Positive sequence network. Okay. So if you know you're only ever going to look at 3-phase fault, then you only have to make the positive sequence network, right? And you could tell because right here, this box, the 1 right here represents your positive sequence network. This is a Thevenin's equivalent of the network. Thevenin's equivalent. Okay. That's what we're going to find for each network. And then you can find your fault current here. A phase-to-phase fault is a little bit different because we're going to use a positive sequence network, W, and the negative sequence network. Because a phase-to-phase fault inherently unbalances the system, because let's say B and C phase gets faulted, A is still healthy, we're going to need to look at a negative sequence as well to see how unbalanced the system gets. Again, notice the one right here, this denotes positive sequence network for this box. And then this box right here represents our Thevenin's equivalent of the negative sequence components. Notice that we're going to put them side by side and connect them together. Okay. We might have a double line to ground fault because now the ground is involved. We're going to need our zero sequence network. So here we're going to have positive sequence network, a negative sequence network we're going to have to build, and a zero sequence network we're going to have to build. And again, here is one. So this is your Thevenin's equivalent for the positive sequence network. This is your Thevenin's equivalent for the negative sequence network. And this is your sequence, your Thevenin's equivalent of the zero sequence component. Notice all of these are put in parallel. Right? And lastly, we have single line to ground faults, which again uses all three networks. You use your positive sequence, your negative sequence, and your zero sequence networks. For a single line to ground fault, this is in series. But as you can see, depending what type of faults you're going to look at. Now, remember, single line to ground faults are majority of all the faults in the power system. So typically we end up looking at that. So you're going to most likely have to build all three networks. Okay, but again, this is your positive sequence network, this is your negative sequence network, and this is your zero sequence networks. This when you put all into series and then you do your calculations. And we'll go over the calculations later on. Okay. So again, so far building three networks together. So build a positive sequence network, negative sequence network, zero sequence networks, and then put them together in this configuration, and then just do either loop analysis or node analysis to find your currents. Okay. So that's this one right here. So let's go ahead and start talking about building networks, because that's the hardest part. Once you build the networks, you're going to be set. All right, so here, for example, we have the generator, a step-up transformer, and a transmission line, right? Some of the rules for building a positive sequence network is you find a line to neutral system diagram, which is a one-line diagram. You want to include all the generators. You want to use your XD double prime of the generator. You want to use your X1 positive sequence reactance for both transformers and transmission lines. And then you want to reduce impedance as much as possible to the fault point. Okay. Now, here, let's assume the fault is at the remote end of the transmission line. So we're going to put a fault right here. Okay. So we're going to build our network based on this fault point. It's one thing that's very important to note is when you move this fault point somewhere else, you're going to have to rebuild the entire network, because the starting and ending point of the Thevenin's model is going to be where your fault is. So let's go ahead and do that real quick. So here we have, well, let's just keep it like this. We have a generator. I like to start my generator down here. So we're going to draw our generator. Okay. We're going to follow the one-line diagram, but the generator has an internal impedance inside it. So we're going to put XD right here. So this is our XD prime, double prime. Okay. We're going to always use a subtransient reactance for our fault analysis. We're going to go up, we're going to hit the first bus, and we're going to come to a transformer. Now, because remember last week or before, we're looking at per unit values, we're using a per unit system here, so we don't need to draw a high side and a low side. We could just interpret this transformer as a pure impedance. And we're going to call this XT, and I'm going to write a 1 to denote positive sequence impedance. So we're using this one right here. We're going to go to the next bus right here, and we're going to have a transmission line. Now, notice the transmission line has this X1 impedance or its positive sequence impedance. We're going to use that one as well. So this is going to be X1 for positive sequence, L for line. Okay. And then we're going to hit the fault point right here, F. Okay. Now, additionally, I like to draw the neutral point right here because this is our neutral coming out. and we're going to put a dot right here and call this our neutral point. So this is our F1 to Fn. So this is our symmetrical, this is our Thevenin's equivalent of the circuit, and looking into the circuit is going to be our Z1. Okay. And if we crunch this all together, it's going to literally look like this, F1N1. This is equivalent to that box we saw at the previous page. Okay. Where this point right here is F1, and this bottom point is N1. And your job is to put a source inside this box and combine all these impedances together, right? In this particular case, it's very easy because there's series level impedances. So you just add them all up in series. And that will be your total positive sequence network. Okay, so just remember those 4 rules when building any positive sequence network. Now we're going to go, let's do the negative sequence network. Oops. So here, let's look at negative sequence. Let me scroll down just a tad bit more to give me some more room. Now, one rule you got to remember, generators only ever produce positive sequence voltage. I'm going to repeat that, very important. Generators only produce positive sequence voltage. What this means is a generator will always be a balanced voltage. If the source is unbalanced, it will produce negative sequence voltage, but generators inherently are purely balanced. So you must ignore all power sources for all generators for your negative sequence networks. Then you will use XD double primary reactance. If it has a negative sequence reactance that's different, you would use that. You use your X2 of all your transformers line impedances, and again, you reduce impedance as much as possible to the fault point. Okay, so let's same fault point as before, but we're going to look at our negative sequence network. So it's going to be F2. So again, first, I would always draw the generator for a positive sequence, but because it's negative sequence, I'm not going to draw a generator. Instead, you just draw a line. I like to draw a line just to remind myself this is where V, the voltage should have been. But again, negative sequence, we ignore the voltage completely. We go straight to the generator impedance right here. We call this XD double prime. We're going to go move up. We're going to hit the bus. We're going to go through the transformer, which is now just an impedance. We're going to call this X2T. So remember, we have to use our negative sequence impedance, right? You can't mix and match them. Everything's going to go wrong. We're going to hit our bus again. We're going to hit our transmission line. We're going to use X2 of the line, and then we're going to hit our fault point, F2. Now, on the bottom side, this is where the generator should have been. We're going to go and pull out the neutral and bring it all over here and call this N2. Okay, so again, this is our Thevenin's equivalent. We're going to look in with a Z2 equivalent. And then in this case, there's no voltage source, so you're just adding up impedances. This is equivalent to our new box model, right, of F2 on top and N2 on the bottom. And we're going to draw them out. So we're just literally taking this negative sequence network, combining it, and placing it into this box with a new impedance. Okay. Now, we could do the same thing. So that's 2 out of 3 done. Let's do the negative sequence, zero sequence network. Now, I'll be honest, the zero sequence networks is by far the hardest because you have to take into account the grounding terminals of transformers and some generators. Okay. Now, let's just go through each one. So first off, build zero sequence impedance network. All generator voltages are ignored. Again, you just short them. Use XZG for any generator reactance. Use X0 for any type of reactance. I believe this negative should be 0. Right, that needs to get fixed. Transformer zero sequence chart has to be drawn correctly. This is a big one. Previously, we just drew an inductor for the transformer, but now we're going to have to actually draw a network. Now, depending on which type of connections we have, some of them will be open circuit, some will be closed circuit, right? If you have any ground impedance, you should add that in as well and then reduce this normally. Now, I know this looks confusing, but the idea is If you have a transformer, you could literally take this point and this point, take it out and put a new set in right here. And that will be your network. So a Y to Y transformer is just the same impedance we always known. A Y delta, you can see that we have impedance and then we shunt it to neutral, but then the delta side is open, right? And then you have all different sorts, okay? So best thing to do is just go by the chart and just remember these are your boundaries here and here and here and here, and then just hot swap them into your network, okay? I'll be honest, majority of your work is probably going to be these two. Those are the more common ones, but you might see the other ones as well, okay? So kind of a little confusing, but let's see it in action. It'll probably make more sense, okay? So here is a zero sequence network. Now remember, we have a delta to Y transformer, so I pretty much brought in the network for us, right? It's literally just the previous network. I did transpose it to match our delta to Y connection right here, okay? So just to make sure that, you know, very, very clear. This is point A. This point A is right here, A. This is point B. This point is right here, point B. So later we have a delta to Y transform. We're going to hot swap this network in the bottom. Okay. So let's go ahead and look at our rules and, you know, build a network. Okay. So first off, we have the generator. Let's use purple. So remember, I'll always start with the source. The source isn't present because it's zero sequence network. So I just draw this big line to say, hey, this is where the generator should have been. It's not there anymore. Okay. And then we're going to go up. We're going to hit our XD double prime impedance. I didn't specify per sequence. So it's just the same for all of them. Okay. We're going to go hit our A phase. So here, right here, we have that transformer. We're going to have to put something in. Okay. Now, I'm going to go ahead and label this point 1. This point right here, which is equivalent, is this point right here, 1. Okay. So according to this, we're going to keep on going and we're going to dead stop. Now on the bottom side, on our neutral, we're coming out, we're going to hit the transformer. This point down here, this is 2. So on a neutral point, I'm going to hit a 2 right here. So you can see how I'm kind of hot swapping that model in. And this model says we're going to keep on going and we're going to go up. And then we're going to have that inductor right there. Like so. Okay. So this is what the rest of the network is going to be. Now, that kind of looks weird. Let me redraw that. Okay. So let's draw it like this. Notice that big gap we have. And then an inductor. And we're going to keep on going. Now to close the loop, here we're going to have 2 points. We're going to call this 3 and 4. These 2 points are the end of our network, which is 3 right here and 4 right here. Okay. And then that's equivalent to the B bus on the top. So now we could actually go out of the transformer and then hit our bus right here. So technically where this A is, this 1, I should write I should write the bus on it like so. Okay. This is equivalent A is equivalent to 1. 3, we left the transformer, we hit bus B. So let's move that 3 over and let's put the bus in its tap place like that. There you go. Okay. And just across, remember, this is bus A, this is bus B. Okay. So we really took A and B and we swapped over 1, 2, 3, 4 points and we just put in that network right there. Okay. Now this impedance right here is a transformer impedance. This is going to be our X0T. And then now that 1, 2, 3, 4 box is put in, we're going to keep on going with the rest of our network. Our transmission line is going to be next. We're going to put in the reactance of the transmission line. This is going to be X0L because there's 0 sequence. On the neutral point term, on the neutral wire, we're going to keep on going till we hit the end of the network. So at the end of the network right here, we're going to have a fault point. we're going to call this F0, and then we're going to have a neutral point down here and 0 for the fault to flow through. Okay, so this is our combined network. It looks a lot messier than the previous one because that delta Y transformer. But notice that little 1, 2, 3, 4 box we put in, it's just hot swapping whatever that chart tells you to do. Now, here comes the Thevenin equivalent. Remember, we are still looking into the network and we're still trying to find Z0. Now, how we're going to figure it out? What's this appendage over here doing? Remember the rule of Thevenin's equivalent is current is going to enter a let's write. Current is going to enter one point, we're going to call it F0, and it's going to go through, and then it can't go anywhere else, so it's going to go down this branch, and it's going to go back to the source. Okay. Now, if somebody asks, will current ever flow through here? This is going to be 0. And the reason why it will never flow through this branch is it has no return path. If the current keeps going, where is it going to go? It's going to dead stop at this appendage. So there's no current flowing through here. It's not even worth drawing an arrow right there, right? I might keep this I0 just to remind myself. Okay. So here we have our current flowing through. We'll call this I0. And now when we do our Thevenin's equivalent, we could pretty much just take this whole side and just kind of exit out and ignore it. We don't need it anymore. Because no current's going to flow, the impedance will not play a factor into our network. Okay. So now it's literally only two things we have to add together. So it's X0T plus X0L to find our zero sequence network. And then remember, this ends up being that box. Okay. This is F0 and N0, and we're coming out with our terminals. Okay. And that's going to be put into the network. And we draw as F. So again, some people might ask, well, what happened to the generator side and everything else? Well, remember zero sequence? Last time we made a rule. Didn't we say in a rule that zero sequence never flows on the delta system? Look at the transformer. The left-hand side of the transformer is a delta. That means it's a 3-wire system, so then no current will ever flow on this side for the zero sequence network. So look over here, you see how we broke the circuit with that delta? No current's ever going to flow. Exactly what we said before. No zero sequence current never flows in the delta system, and the left-hand side of our network is delta, so it gets thrown out of the zero sequence network. Okay. So that's our three systems put together. We crunched them into boxes, and now we would theoretically go on to the next step. But before I do that, I want to take our standard 20-minute breaks to get you guys to do some practice problems. Here, I want you to build the network, right? I went through all three different types of networks. I showed you the rules to build it. So here's your positive sequence, negative sequence, zero sequence. Use those rule sets, and I want you to actually calculate your positive sequence impedance fully. Okay, so I would draw the circuit, number crunch your positive sequence impedances, do the same thing for negative sequence, draw your negative sequence network, number crunch it to a Thevenin's equivalent, and do the same thing for your zero sequence network. Draw your network, number crunch it, and you should have one impedance at the end. Okay, so why don't we go ahead, take a 20-minute break to get these three sequence networks built up. We'll come back, check our work, and then use it to figure out our fault current. So see you guys in a little bit. All right, welcome back. So here we're going to check your sequence networks that you've built. So looking over here, we have a fault at the remote end of the transmission line. It's the same network as I was building earlier. And if you just look, we have a positive sequence voltage we put in. We have a XD double prime, our T1 our positive sequence transformer impedance, our positive sequence transmission line impedance, 25%, 10%, 12%. You just add them all together because they're in series. Our Z1 is, now don't forget a J because this is all inductors, reactors. So J, add them all together, I got 0.47 per unit, right? Or you can keep the percentage and I'll move the decimal place 2 places. Okay, so 0.47 per unit is the result for the Z1 network. The Z2 network, so your negative sequence network, again, we're going through and we're building our network impedances. Here, we're going to use XD double prime. This is 25%, right? Here I have transformers, all your impedances are same, so it's 10%, that's easy. And this last one, this is 12%. So in this particular case, our positive and negative sequence impedances are same, which is it's common sometimes, right? And sometimes it might be different. Depends how accurate you get your information from your manufacturer. Again, add them all together, you can get 0.47 per unit for your negative sequence impedance, right? With the J. Okay. And then, of course, the harder one is our zero sequence network. Here is, we have a fault point right here again. And then remember that the delta side is not used, so it's really just the transformer and the transmission line. So the transformer, again, is 10%, but the transmission line is 40%, so it's a little bit higher there. So because the way the current flows in, it's never going to flow on the delta side. We're just going to hit 2 transformers and go back out. 2 impedances and go back out, so we just need to add 2 of them. So we're going to get J 0.5 per unit. So in the end of the day, remember, we just made 3 networks: positive sequence network, negative sequence network, and zero sequence network. Okay. Now the big question is, what do we do now? All right. So if you remember at the very beginning, we talked about finding individual networks, impedances. Now we're going to add them all together based on the chart. Now, for example, here we're going to keep it easy. Let's just look at the 3-phase fault of the system. So the same fault point we've always been pointing at the end of the transmission line, let's figure out a 3 line to ground fault. So this is 3 line to ground fault. Okay. So for a 3-phase fault, all we need is the positive sequence network, right? So we have the box with just the 1. So we would draw our circuit out. Now notice the way this particular diagram is shown, F1 is at the bottom and N1's at the top. So we just got to kind of flip our model around. So N1 is going to be up top here. We're going to come out, we're going to draw a voltage source here. And then we're going to go down and we're going to have our Z1. Okay. And then this will be our F1 point. Okay, so the way I draw my circuits, F1's on the top and N1's on the bottom, but this particular diagram, they flipped it, so we just got to flip our Thevenin's equivalent over. Okay, now one thing to note is, oh, sorry, let's keep on building our network, forgot. We do have a ZF if we had one, so let's add that in. Now, fault impedance from the ground is typically resistive, so we draw a resistor, ZF. Now, I gave you some information. We're going to assume 0 impedance, so this is 0 ohms, so we don't have to worry about that. And then our voltage is 1.0 per unit, so our V1 voltage is known. Okay, now Z1, we already know this is J 0.47 per unit. You calculated that previously. So now we're taking what you did and we're using it to figure out fault current. Now, where's the current? The current comes out of the fault and it goes all the way down back to the neutral point like this. We call it I1, right? It comes out the positive terminal of voltage source and goes back in. So you see the arrow right there. So all we got to do is just, well, what's my fault current? I1. Well, in this case, I1 is just 1 voltage source and 1 inductor. We're not using the resistor because it's 0. So it's pretty much just Ohm's law, right? There's nothing more fancier than just straight up Ohm's law. So we do V1 over Z1. Now V1 is 1.0 per unit, right? I didn't specify a phase angle, so we assume 0 degrees. Our Z1 is J, 0.47 per unit. So when we number crunch this is going to be 2.13 at an angle of negative 90 degrees per unit. That negative 90 degrees comes from the J on the denominator. Okay, so that's our positive, and this is positive sequence current that we just figured out. Okay, so that's from our network. Now the next question will be, well, what's our I2? What's our negative sequence network? Well, guess what? There is no negative sequence network. So no negative sequence network involved because it's a three-phase fault involved, right? Three-phase fault is inherently balanced, so we don't need negative sequence. So if there's no negative sequence network, there's no negative sequence current. So this is just 0 amps. We just ignore it. Okay, same thing for zero sequence. There's no zero sequence network in this particular case. No zero sequence network involved. So this is also 0 amps as well. So in this particular, in a balanced fault, you just use positive sequence network and positive sequence current. Okay, if this is anything besides a three-phase fault, we'd have to add in the other networks and sequence components. You'll have to calculate I2. You might have to calculate I0. It's going to get more complicated. Okay. So now we have I1. We're not done yet. We need to find IA, IB, and IC because at the end of the day, I need ABC fault currents in the power system. A positive sequence current doesn't really tell me much in the power system itself. Okay. So now we need to convert from symmetrical components back to phase components. This is what we did the last class period. Okay, now just as a carrying over from the previous slide, I1 is 2.13 angle negative 90 degrees per unit. I2 is 0. I0 is 0 as well. Okay, this is amps. Actually, no, technically, this should not be amps. We're in per unit system. So I should write per units, per units, per units. I even think I messed it up here. Did I? Yes. So let's correct ourselves. This is, if I'm gonna draw anything, it should be per units. Okay. We're not in amps yet. That's A phase, B phase, and C phase are in amps. Okay. So here, let's keep on going. We have IA. Now, if you remember the matrix used before, IA is just adding I1 plus I2 plus I0 together. So it's just 2.13 angle negative 90 degrees for A phase plus 0 plus 0. This is 2.13 angle negative 90 degrees per unit. So that's our A phase current. Okay, this is physically what's going on. What about B phase? Well, we could do the same thing, but the big difference with B phase is there's that alpha squared operator. So this is going to be 2.13. We're going to, it's negative 90 degrees, but we have that alpha squared operator, which puts a negative 120 degree shift in there. Remember, the alpha squared is in here, right? The other two are 0, so it doesn't matter. So we're plus 0 plus 0. This is 2.13 with an angle of negative. So see, negative 90, we're going to add them together, it's negative 210 degrees per unit. Okay. And then lastly, we could do IC. So this is going to be 2.13 angle negative 90, but we're going to have an alpha operator. So this is the standard alpha. And that'll be positive 120 degrees plus 0 for the other I2 and I0. So this would be 2.13 angle, so negative 90 and 130, so that's positive 30 degrees. Okay, so this is our three-phase IA, IB, IC currents in per unit. Now notice, let's do a check. Magnitudes are the same, right? So all magnitudes are the same. What about phase shifts? Between here and here, we got a negative 120-degree phase shift, right? Yes. Between here and here, do we have a negative 120-degree phase shift? Well, negative 210 and negative 120 is negative 330, right? And then we can always add 360 to that, which will be positive 30, which is what we have down here. So yes, it checks out. So 120-degree separation. See, it's good to check your work like this. So a three-phase fault is balanced because the magnitudes are the same, 120-degree separation. Now, we do have a negative 9-degree phase shift on everything, and we have 2.13 per unit current, which is a little bit high, but everything else checks out. So this is a three-phase fault, right? If we're going to do another type of fault, we'll get different types of answers, okay? So if we really wanted to, there's one more step that we would take the per unit and convert it back to actual amps in the power systems. But for fault current, sometimes it's more effective to keep it in per units than actually put it into hard amps. It depends on what you need based on what type of calculations and what you're looking at, right? So for now, I'll just leave it in per units, but there could be that step of converting it with a base back to actual amps, okay? So that's pretty much the start to finish of finding a fault analysis. Now, I'll be frank, this is the easiest, probably the easiest example I could give you on fault analysis because it's three-phase balance. Everything else is going to be more complex, okay? So, and you know, this is where that textbook comes in. It could show you a lot more complex ways to do things. And, you know, I'll be honest with you, in today's world, I mean, we have computer simulations to do most of this work for us. It's good to know the basics and know how to get there. But when you have a power grid half the size of California, you're not going to be doing this by hand. You're going to be using Aspen or some other program to do the calculation for you. But it will spit out positive sequence, negative sequence, and zero sequence components and currents. And you do need to know what that means. So you might not need to know the process, but you have to know the end results and how to analyze that. And seeing it in action here will hopefully give you a better idea of what this positive, negative, and zero sequences actually mean. Okay, so let's kind of conclude everything we've done. So first off, we built the positive sequence network, right? That pretty much you figure out what Z1 is and V1. That's what you try to figure out. For the negative sequence component, remember we got to find Z2 and there's no voltage involved, okay? So if the Thevenin equivalent is only impedance, it does not include a voltage for negative sequence. Zero sequence or Z0, you need to figure out, and no voltage. But we must include our ground network, okay? You remember that transformer chart with the grounding of the transformers, delta to Y's? That's what I'm talking about. The ground network needs to be included in your zero sequence component. Now, using all this, what can we figure out? Well, we could figure out either our, based on our fault type, either line to line, single line to ground. So that's one line to ground. Or maybe if it's rare, two line to ground. Depending on what you are, you need to look at the network chart. So there's a chart for each one of these, and configure or combine all your networks based on that chart, whether you put them parallel in series. Literally just look at the chart, throw in your networks, and then crunch it up into hopefully one inductor, one resistor possibly, and a voltage source. And then you just do Ohm's law. Okay. After all this gets put in, what do you do next? The results are symmetrical components. You need to revert them back to phase components. So remember, you're going to get I1. Let me write that a little better. So your results of your sequence of networks will be, you'll get I1, you'll get I2, you'll get I0. this all needs to get converted over based on that matrix to IA, IB, and IC. And again, optional if you will be in per units. If you want actual values in amps, you do an optional conversion through your base value. You get finding your base of that that part of the grid and multiplying by per unit to your base. Okay, so that's pretty much the whole shebang about symmetrical components and just a little introduction to fault analysis, right? So I think that's good enough for this week. We're going to come back next time and start talking about more protection. So you guys take it easy and we'll catch you around.